So I met, I'm blanking on his name now that I'm in front of everybody. Who is it? Mark? Who's the postdoc here that I... Sam, of course, right. So I met Sam a few months ago, and we talked, and seemed to have like a lot of good things to talk about, and he was working here, and I've, of course, known of your guys' work here for quite a few years, through GNU Radio, through my work at Virginia Tech when I was doing a PhD there in cognitive radio. And I knew that Eric Blossom, the former head of GNU Radio, had a good relationship up here, so it just seemed like a good fit. I live in Philadelphia. It's not too much on my way to come up here, and it seemed like a good idea to come up and introduce myself and get to know a few of you guys and see what's going on here, and just go over some of what we're working on in GNU Radio. A bit of an introduction to GNU Radio, but I think most of you are probably at least somewhat familiar with the project or the program. But just to kind of get us on a level playing field, I'm going to go over the basics anyways. And then it's a fairly long presentation. Most of it's kind of recent results, so I just kept adding to it as I was going through. So we'll see how far I get or how quickly we want to get through some of the more advanced stuff. But just to start with, GNU Radio, for those of you who don't really know or haven't really programmed in it, it's designed as a streaming signal processing system. And I make sure that we point that out. We're real-time and streaming. It's not as, you could almost look at GNU Radio as GNU DSP. It's a library of digital signal processing algorithms and blocks and programs. But it's more than just a library of those. In fact, it's probably more importantly more than a library of those. It's an application framework that allows you to connect those blocks together and stream data through. So any signal processing application that you have, we're trying to build a platform that allows you to interact and work with it. So basically, to get to the point is, we have a ton of the blocks. But, it's the whole GNU Radio thing, that's another thing that I like to point out. As we call it radio, people think that it's focused just on radio. And that's where I think the misnomer can kind of come into play, and try to figure out like a better way to describe it, because we're not interested in just radio applications. I mean, that's probably the majority of what we're interested in, but there's plenty of other signal processing problems and problem spaces that a framework like GNU Radio could help. Could play in and could work with. So it's more than that, but this is probably its biggest feature as opposed to some of the other platforms or products out there that have signal processing blocks. So to create this kind of streaming, real-time streaming system, we developed this flow graph, and so to kind of walk through what the flow graph kind of concept is, the high-level data structure of GNU Radio. You start off with a source. You have to have something that produces bits or symbols, or as we call them, kind of generically items. So there's a stream of items, and this could be a complex sample, or it could be a bit of information, or it could be a byte, or even a packet if you wanted to represent it that way. So you got to come in from somewhere, and GNU Radio offers you the ability to pull in data from all sorts. This is just a short example, so you could just read stuff from a file. You could bring it in from an audio source, like a microphone. Other programs, so you can kind of tunnel messages through into GNU Radio from another application layer. Or radio hardware, so if this is a receiver, you have a radio receiver, that's acting as your source of samples that GNU Radio is then going to act upon. And then on the other end, you've got to have someplace to put these bits. So this is the sink. And so again, you could just dump them to files, you could output them to a speaker if it's an analog or acoustic waveform. Again, tunnel it out to other programs, other radio hardware. So if the radio in this case is a transmitter, you can push items out that way. Or GUIs, graphical interfaces. So if you want to visualize your signal or interact with it some way, we have that. And then in between, you get to construct your flow graph. These are all of the signal processing blocks that you can put into a GNU Radio system. And I tried to represent it in a way that shows you that you can have one block have outputs to multiple other blocks. Blocks can have multiple inputs or multiple outputs for certain purposes. You could have multiple sources or multiple sinks. You know, if you wanted to view the signal and store to a file, you can have multiple sinks. The one thing that you can't have is a feedback loop. So it's a digraph. It's a directed graph. It goes one way. So we don't allow feedback, and there's a very good reason for that in GNU Radio. The way that we do the handling of the streaming data. And so when you want to do feedback, when you want to do phase lock loops or carrier recovery loops or anything like that, usually that's within a block. So you can feedback within here all you want. You just can't go from one block to another. And hopefully as I explain what goes on underneath, that'll become a little bit more obvious as to why and what's going on there. And I'll try to bring that up when I introduce that. And this is part of the reason why is because we've optimized the system for throughput. So there's a dynamic scheduler that's going on that's moving samples from one block to the next down this flow graph data structure. And so we try to move as many samples as possible to maximize the use of the bus bandwidth, but minimize the overhead of copying data from one memory to the other, and instead focus on doing the computations on large amounts of data at one time. I did recently throw in an ability to set the maximum size of the samples you can transfer, because otherwise it tries to build up as big a buffer as it possibly can. 32,000 items. Well, 32,000 items at 9,600 bits per second is a fairly long latency time that people don't really like. So if you're working with small bandwidths, data rates, or if you're working with tight latency, there's I call it experimental because it hasn't really been used that I know of greatly in real-world applications. So we don't really know its effect in the real world. In my lab experiments, it works great, but my lab experiments are never good enough for me to know that it's a real working system. But we tried to say that if you want to control latency, here's a new way to approach that. And so what I mean when we move chunks of data, as I said, we're in that flow graph structure, so there's producers and there's consumers. So one block processes data in whatever way you want. Maybe it's just multiplying it by a scalar or doing a filter operation. So you're going to pull in data. He's going to produce a segment of data for the next guy to consume. So we're going to pass over some n number of items. And that's the n that we capped if we're trying to control latency. Or it's the n that we let grow for as large as possible, because anytime you do a memory transfer, you're incurring overhead in your processing. And so to minimize that, you want to do as big a chunk as possible to move across there, and then process that internally in the block. So this is really why that n, that large n, is why we don't allow feedback in the loop. Because if you're thinking about trying to construct a phase lock loop, you've got your phase detector, your low pass filter, and then your voltage controlled oscillator, your numerically controlled oscillator. Well, if each one of those is a discrete block in GNU Radio, and you're passing 32,000 items along at a time, what does that feedback loop look like? You're so out of date by the time you've corrected that NCO that it's meaningless. So unless you want to pass one sample around at a time, which is going to incur a huge amount of overhead, it's really inefficient. And so we've just said, we're not going to do that. We're not going to support it. If you want to have one sample feedback, do that inside of your block. So that hopefully is a little bit of insight into what the structure is and why we've decided to go certain ways with the code. The other thing to think about is in software radio and really in any communication system, sample rate changes are really important. So multi-rate signal processing is a huge deal. And so generically, GNU Radio supports 4 abstracted blocks, signal processing kind of paired class blocks. So the standard one is the one-to-one. So you have one sample input, you produce one sample output. Then you have the interpolators. So you come in with one sample and you produce n samples out. So you're interpolating your signal in some way. You can think of all of these in terms of filter operations. If you think of an interpolating filter as you're adding samples to a stream. So the inverse of that is the decimator. So you bring in n samples, you decimate it down to one sample. And then there's the generic block, which allows you to bring any number in and produce any number that you want out based on whatever relationship you want. So that's probably the hardest to work with when you're actually constructing a block, but it's also the most generic and often useful for really complex tasks. So that kind of helps you understand a little bit about what goes on internally in our flow graph structure and in our block creation system. So going a little bit farther into how we look at this code, all the signal processing is done in C++, but we wrap it into Python blocks to expose it at a higher level language layer that allows you to kind of quickly and easily construct your radio application or your communications application or whatever you're trying to do. We don't do any signal processing in Python. Python's a great language for quickly constructing stuff, for demonstrating, for evaluating, or for connecting GNU Radio systems together. It's a brilliant language for a lot of reasons, but it doesn't do computation like C++. Optimized, hand-coded C++ does. So we never want to have that really to be our, in the pipeline of samples. So we do all of this in low level in C++, as optimized as we can, build the library out of that, and then wrap it into Python to give the users a little bit kind of a leg up as far as accessing GNU Radio. This scares off a few people. For one thing, they think first that we're doing all of our signal processing in Python, which is just completely untrue. Also because it can be a new language. Often we get people coming from, to simplify things, we get people from two domains. The programmers who want to create radio applications, and the radio engineers who want to use SDR to kind of help them and do their work. The radio guys, the engineer guys, don't necessarily like to program, and the programmers don't understand the physics and the real-world constraints of the radio domain. So we're constantly trying to balance those two communities as much as possible and try to engage both those communities. And few of us have the ego to think that we can do both, or at least understand enough of both to bring them together. But this Python level kind of concerns a lot of the engineers coming to the project, saying, well, I barely know C, or I've been doing C++, I'm not a programmer, I don't want to learn a new language. To me, Python is about the easiest language you can start programming in, especially with all the examples out there. It's a great community for help, for examples, for the Python cookbooks. All of those things out there really give you a huge leg up in how to use this as a language. Also, I feel like if you know MATLAB, it's a great transition from MATLAB into I'm being recorded, so I'm going to be careful. Into a programming, real programming domain. On top of Python, you may have seen this GNU Radio Companion. This is a graphical overlay on top of Python. The code that's produced from GRC is actually Python code, but it's abstracted in a way that you can kind of place blocks down on a grid, connect them together, the inputs or the outputs to inputs and so on, and then create your flow graph and run it from there. Great introduction to GNU Radio for making basic applications, for putting applications together very quickly. It also has some interaction where you can have sliders or knobs that you can tune. So if you're trying to build up a new signal processing block, and you have a parameter that you want to be able to change, this is a great way to kind of plop down a source and a sink in your program under test, and then manipulate that parameter to see what its behavior actually induces kind of as you're running the system in a simulation world. So we kind of offer all of these, and you can essentially program everything in C++. You can't actually create your flow graphs and your entire GNU Radio application in C++, but we provide these layers on top of it if you don't want to. The other thing that we provide, as I said, it's not just a DSP block library, but we do have a huge number of blocks. Now, you don't have to worry about reading all of these. Slides will be available and everything. But this is just trying to give you an understanding, an idea of what's available. The other thing that we try to do in GNU Radio, and we're constantly trying to improve this process, but it's to help you guys, to help the users create your new signal processing block or your new idea that you can either, if you can't figure out, or if the representation isn't convenient to put all of these blocks together to experiment with your new idea, we have the framework, the the basic ability for you to create a new block yourself and then integrate it into GNU Radio as one of these. And that's what we're constantly doing that ourselves as developers, introducing new things to do, or sometimes combining two blocks together because they just naturally fit together. That's another way that you can do for performance optimization, if nothing else. So we go all over the place: analog communications, digital communications. We do narrowband, and we have some OFDM examples. These aren't like full-fledged out of the box. You're going to run 802.11 OFDM, but it's to show you it's more educational or more tutorial as in how we create in the GNU Radio concept ways to do these digital communication capabilities. As I said, we do feedback loops, but we just wrap them into blocks in order to do them.
Tom, not to get too specific, but with respect to synchronization, for example, does one offer in a block an entire timing recovery application, or do we have to worry about the details of building timing recovery out of the PLL? For example.
Yeah. We actually have a couple of timing recovery blocks, and then of course if you needed your own, because we don't have a Gardner loop timing recovery, but if you wanted to implement that, you would probably start with, we have a Mueller, which is a fairly close equivalent to a Gardner loop. They're all from kind of the same basic analog timing recovery theory. But you can kind of base off of that. Recently, this is a great question, and we might be getting a little too inside baseball here, but recently what I did is Fred Harris, who's from San Diego State, a good friend of mine, been a really great teacher in a lot of ways. He and I went through the derivation of a second order control loop, and I abstracted that to a parent class. So now all of these recovery loops have this parent class of a second order control loop. So now all you have to do is increment the phase and increment the error and give the new error estimate, using those as kind of internal into your new idea for a timing recovery block. But then I also used Fred's timing recovery algorithm in his book that's based on the polyphase filter bank timing recovery. That's fairly new introduction to GNU Radio, and works much better than the old analog implementations. But so there are again, it's we give you what we think are the good implementations, which could just serve as reference designs if you have a new idea or a different idea for timing recovery for a different application. Well, before I move on to the community, are there any questions more about kind of the basic structure?
Of the digital modulation capabilities, these are transmit continuous stream at the moment, or is it just receiving a packetized format?
It's a little bit of the packetized format. We support it, but I'm not going to tell you that we support it very well. You can discontinuous stream stuff. We do have this famous/infamous program called tunnel.py, which actually connects you to the networking stack. It creates a virtual network interface that you can then actually transmit packets across, and the transmitter will wait and transmit bursty packetized frames. The receiver, while it works, still needs some love and care.
I don't mean actually connecting it to a real packet traffic. Can it say I create a packet format on my own, transmit, and have the header recovered?
You can. Again, we haven't really abstracted it to the point where it's generic enough, but we do have that capability. This is one of those things that's just kind of been on my shoulders for a while, which is to create the abstract concept of a frame, so that you could specify your own header, your own frame structure, put on the proper bells and whistles. Because right now it works, you can do it, but it's a little CS to really, you gotta follow a lot of levels of hierarchy to do it yourself.
CS can mean many things to many people.
Computer science, in this case, very computer sciencey way of implementing it.
What?
Yeah.
Carrier sensor.
Carrier sensor, checking something already.
Yeah, not compressive sensing, not carrier sense, but yeah. So it's very computer sciencey way of doing things, which again, I got into it this morning with some of the students here. There are some times where once you've implemented it, you're blind to how hard it is for other people to read your code. And so it's almost like it needs some fresh eyes, because Eric and I designed this layer structure years ago when we thought it was great, and then nobody else can seem to follow our code. Not because we're great, but because we just did it in a way that's so obscure but we don't recognize how obscure it is. So I'd kind of like fresh blood to come in and rethink how to abstract it in a way that's usable, that's malleable by new people. But as I said, the digital receiver also needs a little bit of work, and this is kind of imminent on my chopping block to attack, which is the bursty receiver structure. Because we do a lot of the recovery loops, but they just tend to be a little slow. So if you're streaming data, maybe you'll miss the first packet, usually not, but maybe. But once it's locked on for a while. And but if you then break that communications and you just start introducing noise, your carrier recovery loops go crazy, and then they have to go from scratch to relock on the next time the bursty packet comes in. It's not the right way of doing things, and actually the last couple slides of my talk will reintroduce this concept and what we're hoping to kind of to use to solve the problem. Just spend a couple of minutes here. I don't want to. I'm not going to belabor this point because I want to get on to the interesting stuff. One of my areas of work since I've been the main developer and the maintainer of GNU Radio, it's been a little under a year and a half since I took over from Eric, but I've been trying to grow the community. So I've been trying to do stuff like help people get stuff on GitHub, use CGRAM, this complementary GNU Radio archive, get your programs out there. These are kind of two different ways of attacking the same problem, which is how to distribute your code and get the community using it. We do have a large participation of our mailing list, and we're trying to improve that and make it. It'd be nice to make it into a real discussion forum. Right now, it's kind of like a help mailing list, which serves one purpose, one really important purpose for our project, which is helping new people come up to speed. But I would like to try to get more discussion of interesting topics of GNU Radio development on there. Let's see, GNU Radio Conference 2011, I do want to plug this a little bit. We started this idea years ago, and when I took over again, I felt that this was a really important part of growing our developers and growing our community, was to get people together, real GNU Radio users and enthusiasts together in the same room for a few days and talk about what's going on, what are their applications, and what are their issues. So we got, with almost no publicity, I mailed to the mailing list a couple of times, word of mouth to a few people. I expected like 30 to 40 people to show up, and we got 55 people, which, like I said, almost doubled my expectations. But more than that, almost doubled the amount of people in the room, and we did not get a big enough room for it. So it's just almost like tightly packed, really high energy room to discuss this stuff. And here's, as you look at the conference website, there's a number, all the presentations are available online, and you can see what happened. But some really interesting application talks using GNU Radio for this quantum optical communication I thought was brilliant. This came out of a friend of mine at Oak Ridge who published, gave a talk on this one. Just a really interesting way of approaching and using GNU Radio. Open source P25, this was really serendipitous. The time that Max came down and gave that talk was right at the same time that Penn had published, we held the conference at University of Pennsylvania, and some of the students at Penn had just published a set of serious kind of security holes and flaws in the P25 standard. And now we got a guy talking about creating an open source version of this, which, idealistically, I think, if we had an open source version of P25, maybe we would have had people experimenting and exploring and seeing these flaws before we had these huge deployments of this system that are now have all these potentially problematic pieces in it. And then an ADSB, which is a aircraft to ground communication standard for relaying information about aircraft. This we started to get really inside of so that was kind of the user, the application layer. Then we went to the developer layer. New schedulers, VOLK. I'm going to talk about this in a second. Stream tags I'll get into in a little bit. And then what you guys are probably interested in, which is network control. Because my vision of GNU Radio is not that people network guys have to fiddle around with the bells and whistles and problems and flaws of the physical layer. If you want to research network problems or MAC layer problems or application layer problems over a wireless channel, we want to provide that wireless channel to you without you becoming experts in the file layer, without you having to dig down deep there. We're still fairly far away from that, but that's kind of my ultimate dream is to provide this open file layer for people to really use and experiment with without having to dive into it themselves. We had a hardware talk, so again, the USERPs, most people are familiar with that. That's the EDIS, Universal Software Radio Peripheral. You guys have a handful of them in the orbit labs. Talk about the new interface to the USERPs, a new hardware platform, very USERP 1-like hardware platform. And then one of my favorites was the graphics processor, so GPU acceleration of GNU Radio. So how do you do this efficiently? And again, it's similar to why we try to move big buffers around GNU Radio. The overhead of moving data from your host to the co-processor, in this case a GPU, and then back, that latency incurred and the overhead of doing that can often negate the gains that you get out of performing the computation on the GPU itself. So they've been looking into, well, how do you do this in a systematic way, and how do you approach it in a way that actually makes sense from a computational standpoint? Like, how do you get the computational win out of a co-processor when you have this bandwidth overhead? So, yeah.
Can you tell me more about Uhd Driver? What does it do?
So what happened in the old GNU Radio code up to version 3.4, we released 3.5 November of this past year, we replaced all of the old libuserp and libuserp 2 with the UHD interface. So the UHD is the Universal Hardware Driver from EDIS. It works with all EDIS products. So whereas libuserp was just for the USERP 1 and libuserp 2 was just for the USERP 2. And then as they tried to grow the number of daughter boards that they were supporting, the product line, they're actually pretty dramatically increasing their product line. And then you have to edit 2 libraries to handle the same new daughter board. They basically said that just wasn't a tractable situation, and then combined them into the UHD. So it's just kind of a relook at how to interface with the USERPs from a more generic standpoint. So now if you have a UHD program written in GNU Radio, you plug in any EDIS product and it will work.
So if I wanted to change the UHD code, what could I make it better or?
Yes, it's GPL, so it's open source GPL. Now, if you're working with the UHD, as opposed to GNU Radio, which we're a Free Software Foundation project, the UHD is an EDIS research project, and so if you have to submit code to them for them to wrap into it. But it is still open source, it is still GPL licensed, so it still kind of has that mentality. So, yeah. But if you have particular improvements for UHD, go to EDIS, because I'm not, we just wrap UHD in GNU Radio, and that's all our not interest, but responsibilities at this point. Is there anything else? So going into, I don't want to run us over time too much, and there's a lot left to be said on all of this. This goes back to my recent comments about wanting to support developers or users of GNU Radio, but I also, basically the intent, because I fancy myself an academic still, is to improve science in communications. And so I think of going from simulation to practice. I don't like necessarily. I understand that there's a role for simulation, and it's the place to start. But if you're telling me that you've got this new great communication system and you've only shown me simulations of it, as I said, it's a place to start. But I really want to go farther. I want to see this stuff work in the field. If it's radio, I want to see it working over the air. And if you're doing simulation, I at least want to see more than a white Gaussian noise channel applied to your on your paper. And so that's what part of what GNU Radio I think can offer is. First, we look at the inner workings of the algorithms. You can go from using the Costas loop So looking into it, or using the timing recovery loop, and to actually looking at the code to see how it's constructed. And sometimes to a more, sometimes to a lesser extent, we spend a lot of time trying to optimize our code so that not only does it work and perform like theory, but that it also behaves properly, has proper bounds checking so that it doesn't run off or cause a seg fault in your system somewhere, and that it runs efficiently on a general purpose processor. So sometimes we don't hit all of those, but that's our goal. So as a student or as somebody who's trying to learn this stuff, people can dive in there and say, okay, this is how it's implemented. I've seen the math, I understand the math, now I understand how the code works. But as I said, I want to see stuff running over the air, real deployments, real development work, real prototypes of new ideas, and done in a scientific method. So instead of just publishing a paper saying, I had this great idea, here's some plots to show the great idea working, why not also say, I implemented this on GNU Radio, it's all open source code, here you can download it, run the same project. Now you can corroborate my results, you can compare your results to my results, actually do the scientific process of comparing ideas. Now I know that that's kind of a pipe dream because we have IP issues and we all want to control our intellectual property. But in certain situations it makes sense, and this is a good platform for thinking about that type of system. And so here's kind of the way that I see progressing through using GNU Radio. So you've got your new modulator and your new demodulator, or just think of it as your 2 nodes of your system. And again, this by itself I don't think is publishable because you just showed me that it's AWGN, and of course, if it doesn't work in AWGN, then you're already done. But so you kind of want to start there, but you really want to go farther. So for one thing, let's replace AWGN with, this is already in GNU Radio, where you can actually set a frequency offset and a timing offset, a phase offset that would be inherent in kind of the different oscillators of your radio. So you're never going to be on the same frequency. The timing, the sample times are never going to be exactly correct on these two sides. So you've got to kind of fix that problem first. You can take that a step farther and put a real channel model in here. We could talk about Rayleighs and Racines and Nakagami's A through Z, but you also have the standard channel models for 3GPP published standards, or 802.11 has a set of channel models out there. If we can plug those guys in here, that's the next step to saying, okay, this is a viable simulation that shows in these given circumstances I've got a working system. This, I think, is really interesting. We don't really talk about this enough at all when we're talking about simulation. Again, going from the theory to the actual implementation, we forget that hardware has problems. The realities of doing communications in any real system has potential problems and pitfalls and impurities that we have to understand. But this came out of a talk that Matt Edis gave, brilliant talk at our conference in September this past year, on what kind of hardware impairments do we have to explain. I think the kind of subtitle of his talk was, why doesn't my signal look like it does in the textbook? Okay, you create a BPSK signal, you send it over the air. Well, why is it, what's going on here? Why am I getting this weird shape to the signal? And part of it is this hardware impairments. And he went the step farther than just explaining what these problems were. He actually created GNU Radio simulations of IQ imbalance and phase noise and DC offsets and magnitude offsets. So all of these things that you can say, okay, if I can understand what is the range of possibilities that my hardware is going to allow me, or given my situation, given my modulator and demodulator, what kind of IQ imbalance or what kind of phase noise does my system require? Based on playing with these parameters in this hardware impairments model, that's That's a really kind of important lesson that we can learn without having to spend the money yet on going to the hardware. Or when we go to the hardware manufacturer, we say, you have to meet these specifications, or I can handle these types of, this type of tolerance in the specification.
Quick question, Tom. Where in that diagram would I introduce interference?
The channel model. That's kind of the generic, the channel, and
Not
maybe it
just
should
the
be.
passive channel, I could introduce something coming in.
Yeah, yeah. So that's kind of, this maybe should be the capitalized channel model. It's all of that stuff that plays into. So not only your multipath, but your.
Could you elaborate on that a little bit?
I'm just thinking of a network with multiple users, and I want to find out, I'm testing my DPSK against different kinds of interference.
Yeah.
And where would that different interference go in?
Actually, I say that, because again, that's just generic. It probably would be better of me if I kind of expanded this out, because all you really, you could have a little adder there with as many inputs as you wanted to. I could make that more explicit. I didn't really think of that particular problem, but it's an important one.
It's
so,
important,
yeah.
I do that.
Yeah.
Okay, fine.
But so then you get to this hardware impairments thing, you prove that, and then you can say, okay, now let me put in the hardware transmitter and receiver, or two transmitters apparently, if you copy and paste. Put the channel in between, like a real channel, the real environment that you have. And what's nice about GNU Radio is, especially as I'm redoing a lot of the examples, I'm trying to decouple the example from the hardware implementation so that it's kind of easy to switch from the code to go from the simulation into your own channel model to just removing that channel model in the code and dropping in the hardware transmitter or the receiver at either end of your simulation. And then you've kind of gone immediately from the simulation world to a real environment, and then see where that takes you. So I kind of like that trajectory of learning how things go step by step in introducing these issues as we go along. Is there anything there? I know I'm blowing through a lot of stuff right now. Is there any problems yet? So this is kind of the state of where we are in GNU Radio. There's a little bit, went through a little bit of philosophy about what I see GNU Radio being useful for and using. This hardware impairments model, it's available on our webpage. I haven't yet gone and actually put it into the code of GNU Radio. One of these days I will actually get around to doing that so that you can kind of out of the box start playing with those situations. And understanding when you see spikes happening in your spurs or harmonics or whatever images happening in your radio system, you now have some ways to experiment and understand those. But I want to go into the future of what we're working on GNU Radio, and I've been talking about this for a while now. The actual use of VOLK is imminent. I actually have code working that I've had to do some changes internally to make it work, and I'll try to explain that in a high enough level to understand why it's a problem and why it took us so long to get to it. But the end goal is that we can use VOLK. So VOLK came out, it's a library that does this, as it says, vector optimized library of routines. So what does that mean? What's our problem that we have to solve? The problem is we're running on general purpose processors, or we hope to, or use whatever processor you have, but we're growing in computational limits, requirements as we try to increment our speed. We're trying to introduce new waveforms. We're trying to do channel coding properly in these types of situations. Every time you add something, this is just one curve. I forgot to give credit. This is Andrew Gee. This came out of our networking presentation at our conference. This is a paper that he wrote and published. But he's just looking at the RX data rate of, I think this is just our benchmark RX code in GNU Radio. And just what's the CPU consumption for different processors as we increase the data rate. But as I said, that's just one factor that we're increasing. If you try to introduce convolutional coding and Viterbi decoding or LDPCs or anything like that, you're going to start to come up to limits on what your processor is capable of doing. But processors have these brilliant little things in them called SIMD. It's called SIMD. It's single instruction, multiple data. I like to think of them as kind of DSP core co-processors inside of your on-die with the rest of your chip. They were introduced back in '96, so if you don't know what SIMD is, you might recognize some of these labels from looking at your the computer that you purchased, back in 2004, and maybe it told you that it was SSE optimized or SSE whatever. It was originally designed and introduced to do multimedia processing, or to help with multimedia processing. Its intent was to give you larger registers to do computations in, so that you could actually fit multiple data into one register and then compute on them simultaneously. So when we got to SSE, the registers, I forget exactly how many there are. There's a lot of registers that are 128 bits wide. So you can fit 4 floating point numbers in there at one time. And if you multiply both of these together using the SIMD instruction set, you're now getting 4 floating point computations for the price of 1. So it's a really powerful improvement to the mathematical capability of handling vectorized information. As I said, it was intended for graphics graphics used in multimedia originally, but it's easy to extrapolate from doing that graphical signal processing to whatever signal processing we want to do in wireless or radio. So there's this whole standard set of libraries here, or not of libraries, but of architects here. This is just the Intel roadmap, kind of. There's other ones. There's the ARM. ARM uses a thing called Neon. The Power PCs, when they were more relevant, had Altivec, which also the cell processor was very Altivec-like, SIMD-ICE programming language. AMD used to have 3D now. AMD's basically following the Intel SIMD performance, so you kind of get 2 for 1 there. But every time you increase to a new architecture, you got this new set of SIMD instructions here. Now, AVX is great. It's 256-bit registers. But now that's totally different than the past 10 years of SSE, where you only had 128 bits. So every time, it's kind of like FPGA programming, where every time you got a new FPGA, you essentially had to redo everything to get it to compile and run. Not as complicated in the SIMD world, but we still have that problem. How do you make general purpose computing when you have architecture-specific instructions like this? How do you get access to it? Problem had been kind of kicked around for a long time. We've never seen anything that really approached the solution that we ended up coming out with, which is this VOLK system. Now, the way VOLK handles it is we don't try to be clever in how we create the SIMD code. We're clever in how we access the SIMD code. So when you write some math function and you want to optimize it for your processor, first of all, you always have a generic. You always have the straight C. This is a C library, not even C++. Straight C implementation of the routine, so a for loop that iterates over all n number of items in your vector, whatever. But then you kind of do architecture-specific, hand-done SIMD. So it's still going in there and coding by hand, but say you're interested in supporting SSE and SSE2. So you go in there and hand code those out and offer those as available as part of the VOLK runtime architecture. And then at runtime, VOLK looks at your processor at its initialization. When you initialize a VOLK routine, just once it goes and says, what's my architecture? What's the highest, best performing level of VOLK handcrafted function that I can actually have access to for my architecture? And then it's going to, behind the scenes, link to that. And now you have optimized code. So if you were working on an ARM processor and there was no Neon code, you would be falling back to the generic code. But then somebody comes along and says, this routine really needs to be optimized. I'm going to introduce Neon optimization code in there. We're going to compile it to libVolk. Once it's distributed and compiled into your system, all of a sudden you go from this really slow generic to this highly optimized Neon version, and you get this kind of automatic speed boost. It's just really nice abstraction without trying to be so clever as to say we're going to solve the compiling issue of SIMD multiple architecture codes. I'm going to skip this. That's just the naming system. That doesn't really affect you guys. So yeah, like I said, it sounds great. It sounds amazing. Oh, we can get maybe 4x, maybe more than 4x speed up in our GNU Radio. Now we can start supporting some serious bandwidths or some really interesting waveforms. So why is it taking me so long to put it into GNU Radio? And the problem comes from buffer alignment. Most SIMD libraries require your memory to be buffer aligned to some amount, 16 or 32 bytes. The way GNU Radio works is, I'm going to give a block this many number of items to process. What I know is at the beginning, the first iteration, all of my buffers are page aligned. A page alignment is like usually around 4K of alignment. You're going to hit that, you're good. You're good from the start. But I'm going to process some number of output items that my scheduler is going to allow me to process. The next time in, this is where that input and output items was. What's my alignment? There's no guarantee that that thing is going to be aligned anymore. So now if you actually try to run this through an aligned version of your SIMD code, you're going to get a segfault. So that was just kind of a non-starter. We couldn't handle this. Now there are unaligned loads in SIMD to get into. They tend to be slower. At least I thought they did. It's not what you want. You want to do the aligned loads for the speed performance. Without getting into the details here, you don't need to know this too much. I tried a handful of things where I tried to kind of put these junk, kind of garbage space in there to make sure that I was always aligned. We're multi-threaded processing in the background. That doesn't work because what if this was called multiple times before you read from it? Suddenly you're reading junk, garbage where that A is. That didn't work. I couldn't make that happen. The solution that's in the process right now, and I really hope that I've kind of taken care of all of the corner cases and should be able to publish it soon, possibly even integrate it to the code as of 3.5.2 is my goal to introduce this. From your block, you're able to look at the alignment. So you're going to set the alignment. You're going to say that my block uses floating point items. So my alignment is going to be based on that. There's a way to query VOLK, by the way. So you can say, so it'll tell you if it's a 16 byte or a 32 byte or whatever alignment. So you don't have to know that in advance. You query it, but you just say that I'm using floats. So that's going to set my alignment properties. Then what you're going to say when you go into your function, when you're going to process your code, you're going to ask the scheduler, is my buffer aligned or is it not aligned? And if it's aligned, which based on kind of the background stuff that I'm doing, kind of using these things down here, I'm going to try to keep the buffers aligned as much as possible. But what I don't want to do is force the scheduler to wait until the alignment occurs. Because if you do that, you're going to incur latency, and it's just you're going to stop up your system, and you don't want to do that. So in that case, I'm going to set the fact that we're unaligned. Then I'm going to come in here and I'm going to say, are we aligned? No, we're not aligned. Let me run the unaligned implementation of that code. And so every now and then you're going to take a slight performance hit because you're going unaligned. The other performance hit that you're going to take is the fact that you have to do this branching operation. Am I aligned or am I unaligned? But again, we're trying to work on the big size buffers, so one branch logic statement shouldn't kill us. Well, that's just what I said. We're trying to keep ourselves aligned, pass the data along as much as possible. We don't want to reduce throughput or latency in the system at all. So we keep going as much as possible, trying to keep ourselves aligned. And here are the results. This was, as I say, this is the low-hanging fruit in GNU Radio. There's a lot there. All of these are type conversions. So if you're coming in from a float and you want to move to a short, you would have a block that says float to short. It's a really easy SIMD conversion to implement. And so in this case, this is the processing time over 1 billion samples. And I just basically counted how long it would take to process 1 million samples through all of these type conversions. These purple lines here are the non-VOLKized implementations. And then the red and the blue, this is where it became really interesting to me. And I think it's an architecture-specific issue. So, as I said, there's an aligned and unaligned loads to these registers. The unaligned are supposed to give you a performance hit. But in this was I think it was just a quad core, Intel quad core. You can see that the red and blues are almost always, except for here, I didn't actually have unaligned versions of the implementation. The unaligned are almost never that much worse. And on occasion, like in this one, I have no idea what's going on there. On occasion, it actually turned out to be better. So the overhead of trying to do the unaligned versus aligned call seemed to kind of not matter as much as I thought it was. My goal is that I actually want to test this on an older processor like my Core 2, and then I have an i7 there, kind of what are the different penalty hits that I take for these types of things. Do I want to go into, I don't want to go into that. There's a really interesting reason why this purple and green are different, but it's way low level, and I don't think I can describe it properly at all. So the last thing that I want to talk, there's only a few slides left here to talk about messages and tags. So the motivating example that I have goes back to the bursty communications process. So this was one of Fred, it's a great paper by Fred. If you really want to know real file layer communications, read Fred Harris's work. And this in particular is a really nice paper. He gives this diagram of all of the different recovery algorithms in your receiver. So automatic gain control, recovering the carrier, the frequency offset, doing the timing recovery block here, and then equalizing is a feedback option. And then for a lot of systems, you want phase recovery as well. Most of these systems work well at different levels of SNR. There are different implementations of the algorithms, or you can change the parameters inside these algorithms based on the quality of the signal that you're getting. So you want to know the SNR, but you don't want every block to know the SNR. You want one SNR estimator that can then feed that to the entire system. Well, if I'm going from here down, that's not too big of a deal because of our digraph concept in GNU Radio. If I want to go from here back, that's a feedback loop all of a sudden, and we don't handle that, and we don't want to handle that. So we've kind of introduced two ways of rethinking a control plane in GNU Radio. And they haven't been publicized too much. There's not a whole lot of code that actually shows them working, but we're working on it. So messages is the ability to just have one guy post a message to any other block. So my receiver pointer here, so this would be my carrier recovery, would have to be told that exists. We're going to post a message to him. We're going to calculate the SNR. We're going to say, this guy and whoever else needs that SNR information, we post a message to him, and then he's going to handle that message and use that information in whatever way he needs to. So this allows us to downstream feed back information to other blocks. So that's one way that we can handle data going back and forth and handling kind of control plane data. The other way is this concept of stream tags. So this is an underlying data layer. So as opposed to data moving from block to block, we also have a control plane of tags. And tags are just a message. It's called a polymorphic type, if you want to get into the details. It's essentially a dictionary of items. That could be anything from metadata to actual data to just logic and control information. So this guy's going to kind of come along and insert tags into the stream, pass them down. He's going to be able to read the tags, and he's going to be able to introduce more tags and kind of keep going down here. So anybody at this side of the data stream, he can just insert a tag into there, and then in the work function of the guy down below, you can say, okay, what tags do I have? Do I have a new SNR estimate? And if I do, now I can make some decisions out of it by just having this add tag and get tags in range. So again, these need to be worked on a little bit more to, again, make them a little friendlier to use. Have more examples that actually implement them so that people can actually, go to the example, see how they were intended to work, then figure out how they actually work, and then hopefully actually make some interesting choices with what we're trying to make available in GNU Radio. So by the end of these kind of things, this VOLK and these message and stream tags, what we're hoping to make is a system that's much more efficient than it used to be, and also gives you the kind of control that's required by currents and developing wireless communications problems. Packetized data being kind of the motivating example there. So that's a lot of information in a little less than an hour. So hopefully some of it was interesting. Are there any questions?